For over 8,000 years, our species has woven a narrative that has attempted to describe the ontological nature of reality. A narrative that, as we've seen, appears as much in the dialogues of philosophy as it does in the natural sciences. But there is, of course, no mystery behind any of this, for, as mentioned in the opening chapters, science is itself a child of philosophy, with all forms of modern thought only being the latest in a far-reaching journey of discovery. The UK's most prestigious science academy, the Royal Society, was itself founded by an invisible college of so-called natural philosophers, who in the 1660s began meeting to discuss a new branch of philosophy that involved promoting knowledge of the natural world through methods of observation and experiment. Indeed, it wasn't until the 19th century that we began referring to these natural philosophers as scientists. Even today, our education systems offer graduates a PhD, a doctorate in philosophy. So though it may seem that these paths have since diverged significantly, we should note that even within our most cutting-edge fields of empirical study do we still find the theories of ancients being tested. So that as new reframes old, do the intuitions of old gain ever more relevance, ensuring the continuation of a dialogue that persists beyond time. However, one particular inquiry that has remained at the forefront across all ages has been our quest for universal fundamentals. A quest that poses a question which happens to run in parallel with our philosophical inquiry into the nature of being and becoming. Is nature fundamentally made of particles or waves? So, before we try to understand the elusive flux and its relationship to consciousness, let us first consult these bygone thinkers and unfold their timeless narrative so that we might better understand why it is that we ask the questions we do. Good morrow, fellow humans. My name is Sean Crowley and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is. It all starts with a deceptively simple question. What is light? Ask a child and you will receive a fairly confident definition regarding a level of brightness. Some children may even suggest energy or even electricity. But even adults tend to describe the nature of light in much the same way. Those of us who remember snippets of our high school physics classes may be able to recall that light is actually an electromagnetic wave. Oh wait, no, it's a bunch of photons, right? Just take a look outside, or even around the room you're sitting in. What do you see? From your perspective, it appears that certain objects are lit up, whilst others are in shadow. Our basic assumption is that certain luminous objects, such as the sun or a lamp, are responsible for emitting this light, which then travels from its source until it reflects off the various surfaces. But if this is the case, then it suggests that some invisible version of the light must also be travelling across the room, and even across the vast stretches of space, only to reveal itself when finally impacting upon a solid object. If we think about this long enough, even this simple assumption can be appreciated as quite a bizarre phenomenon. So odd that we don't tend to appreciate how unintuitive our descriptions really are. And rarely will we give any regard for how greatly our assumptions are being influenced by the last 2,000 years of cumulative discovery. Though it was the ancient Egyptians who first provided us with a description for the nature of light, with their claim that light was the act of the sun god Ra, looking down upon the earth. It is, however, quite fitting that our story shall begin ever so slightly after this, a mere hop, skip and a jump across the Mediterranean, with a group of Greek philosophers referred to as the Atomists. The philosophy of the atom is one which suggests that every sensation, be it taste, smell, touch, and even sight, can be reduced to the impacts of minuscule, indivisible particles which, when combined, create all that we see around us. A universe of particles that exist against a stark and otherwise empty void. And this is the origin of the word later borrowed by modern physicists to describe the atoms of quantum mechanics. As such, one could easily presume that the atomists of ancient Greece nailed it with a hole in one. But though their hunch does resonate with the discoveries of the modern era, there was clearly much in the details left to be understood. For example, the atomists theorized that the sensation of taste might arise due to the various shapes of atoms, where a bitter taste might be the result of jagged atoms, or sweetness the result of smooth atoms. Leucippus, Democritus, and Epicurus each were said to have written much about the nature of the senses, including their own atom-based theories of light. According to what we know of their teaching, it was the belief among these atomists that sight didn't in fact arise in the eye, but instead arose from within compressed layers of atoms filling the air between the object and the observer. The image that one perceives was said to be imprinted within each film-like layer, allowing the eye to touch the echoes of surrounding objects. Certain accounts even suggested that this compression of air atoms occurred due to atoms falling away from objects, a situation that also explained why things deteriorate as they age. However, the most influential theory of light to emerge from ancient Greece was that proposed by Plato. In contrast to the atomized theory of sight, Plato leaned towards a theory of rays, and thus set the scene for the waves v particles battleground that was to persist into the following 2,500 years. But even for the greatness of Plato, there was much left to be understood. What Plato proposed was a refined version of a theory laid down before him by Empedocles. Empedocles spoke of the eye as a lantern that emitted a special kind of fire. This was a sight built upon light rays that were not caught but emitted from the eyes. This idea, along with those embellishments from Plato, Euclid, and Ptolemy, came to be known as the extramission theory of sight, which not only offered a geometrical appreciation of light, explaining the nature of reflection and refraction, but also a model of the universe that presupposed a speed of light, for the simple reason that distant mountains always appeared in our field of vision as quickly as any nearby objects did, thus suggesting that these light rays must be emitted at near infinite speeds. A fairly logical conclusion, given the evidence available. And it was at this same time that another concept relevant to our story was first put forward, this time by Plato's student Aristotle. Aristotle, like his teacher, spoke of a world consisting of 4 elements: earth, wind, fire, and water. However, it was Aristotle who further considered the void in which these elements persisted, concluding that as a fish must swim through the water, and as we move through the air, so too must the planets themselves move through some medium that fills all space. To this 5th element, he borrowed the mythological name Aether, the primordial god of light. Beyond its personification as a god, Aether was the name given to the upper air, being the ideal transient between the solid dome of the Earth's sky and the heavens above. Our own word, quintessential, is taken from this idea, with quint meaning fifth and essential meaning essence. And so the pieces were set. Parts, patterns and voids. Concepts that were to remain unchallenged for another 1,000 years. Whilst many people today envision the Middle Ages as being rather abhorrent, with few gains being contributed towards the human endeavour, this description rarely proves to be the case. However, it is to the east, within the burgeoning Islamic Empire, where such inaccuracies become most evident, as it was during this time that a golden age of tolerance, multiculturalism, education and wisdom began to unfold in the region. A period of enlightenment that not only fueled the Islamic Empire from the 8th century up until the 13th, but which also led to the birth of many ideas that still influence our world today. From scholarly writings on the topic of evolution 1,000 years before the birth of Darwin, to the invention of algebra, this cultural melting pot became one of history's most influential voices. Primarily because, in contrast to the guarded nature of Christian teaching adopted in the West, the holy text of Islam instead encouraged a worldly education, regardless of origin, age or source. And so, under the reign of Abbasid Caliph Harun al-Rashid, a movement began that sought to both acquire and translate teachings from the four corners of the empire, from the scriptures of ancient Greece to Egypt, Rome, Babylonia, India, Persia and China. Indeed, if it had not been for this golden period of enlightenment, we in the West may have never even heard of Aristotle. And whilst the idea of the ether, or quintessence, as it was then referred, remained a mysterious source of alchemical magic, it was in this environment that Plato's extramission theory of sight was re-examined. Abu Ali al-Hasan ibn al-Haytham is known today by many pseudonyms, not least of which the world's first scientist. Though he did earn one other honorary title relevant to our story, that being the father of optics. So the story goes that upon failing to provide his host, the ruthlessly unpredictable Fatim Caliph al-Hakim, with a viable solution to the periodic flooding of the Nile, Ibn al-Haytham, in fear of losing his life to the whims of his host's bad temper, decided that, despite his genius, he would plead forgiveness under a case of insanity. And it worked. Successfully avoiding his corporal punishment, Ibn al-Haytham was instead sentenced to the lesser punishment of a 10-year stay in confinement. However, as devastating as this was, historically it was not for naught, as it was during his time of imprisonment that he had a revelation. Within the dark confines of his four walls, Ibn al-Haytham's mind wandered, moving in and out of the present moment, as one does, until his attention was struck, taken by a stray beam of light shining through a small hole in his cell wall. Upon paying closer attention, he noticed that as this beam came to land upon the opposing wall, it cast a peculiar, yet somewhat familiar image. Though it was upside down, he realised that this image was in fact a reflection of the outside world. Whilst many of us may have simply dismissed the curious effect, Ibn al-Haytham chose to consider the meaning behind this play of light, thus inspiring an idea that came to form the basis of one of his most influential works, the Katib al-Manatzir, known in the West as the Book of Optics. From this experience, Ibn al-Haytham devised an experiment which not only introduced our modern scientific ideals of falsifiability, replicability, and evidence for causation, but which also used such evidence to provide proof for his theory that light must travel in straight lines in the direction of its source. By simply placing a pinhole in the wall of any dark space, he was able to show how light must travel in vertical lines from the upper edge of the outer sunlit image towards the inverse lower edge of the inside dark wall, and vice versa, from the bottom of the outside image up towards the top of the inside wall. Thus, by devising an experiment that restricted a path of light through a pinhole, the outside image would be revealed inverted on the opposing wall, precisely as it had done in his cell. This he called his Al-Bayt al-Muslim experiment, translating simply to dark room experiment, although it is the Latin translation of camera obscura that we derive the name for the technology that it would go on to inspire. And if this wasn't already enough, not only did he prove that light travels into our eyes rather than out of them, but he also went on to explain how the image we see is a psychological one, created within the mind of the observer. In the centuries to come, Ibn al-Haytham's Book of Optics continued to remain the dominant text on light and optics, inspiring the likes of Copernicus, Kepler, Galileo, Descartes, and even Isaac Newton in his own revolutionary work Optics, published in 1704. But it was Newton who would once again change gears in the ongoing wave-particle debate. Being the most highly regarded mind of his time, Newton, without equal, dominated the popular opinion with his own convictions that light must be fundamentally digital. Light, as he proposed, should be thought of as moving clusters of minute corpuscles, tiny particle-like bodies of light that once again floated upon a luminiferous ether. By the beginning of the 18th century, a whole suite of models took the idea of an ether as granted, and Newton was to be of no exception. His own gravitational ether was in many respects modern, as it described a medium through which the forces of light, electricity, magnetism, and gravity could persist. But as scientific as this sounds, the truth was that both the ether and our interpretations of reality on the whole had far from shed their religious foundations. The ether was still considered to be some version of the Aristotelian purity, only now interwoven with other various heavenly influences. As Newton described, the main phlegmatic body of the ether and other various ethereal spirits moved together as a type of universal vortex that was whipped up and set into motion, at first by the immediate hand of the Creator, and ever since by the power of nature. Thus, perhaps, postulated Newton, may all things be originated from ether. But beyond the views of his era, his hypothesis for a particle-like nature of light was firmly rooted in the evidence-based thinking that we today consider scientific. For example, sound, which had long been understood to move through the air in the form of waves, showcased many attributes that light didn't. Whereas sound waves can travel through pipes and around corners, light can't. But even beyond any direct evidence, there was still plenty of reason for the public to assume Newton's authority on the topic. his revolutionary insights had already revealed how white light was actually made up of all the colours on the spectrum, and that not only could white light be split into the 7 hues of the rainbow, but this spectrum could just as easily be recombined back into white light when passing through the crystal prism. A result that inspired the realization that colour must be a property of light rather than of the material objects themselves. It was also at this time that another vital discovery had been uncovered relating to the speed of light. By using Newton's new gravitational constant, Danish astronomer Ole Rømer had been attempting to predict the orbital periods of Jupiter's moon Io. But his concerns arose when these orbital periods seemed to ebb and flow outside of the predictions set by Newton's equations at various times of the year, a fluctuation that risked jeopardizing the validity of Newton's gravitational equations as a universal constant. Rømer's own moment of brilliance, however, came when he realized that the apparent variations in the results had come about as a result of the Earth's own orbit, as well as the finite speed attributed to the light travelling from Jupiter to Earth. And so, by including the influence of the orbits in his calculations, Rømer was able to broadly calculate the time it had taken for the light to travel the great expanse between the 2 planets, providing an almost entirely accurate speed of light. But as reaffirming as this was for Newton's theory of gravity, it did little to support his corpuscular theory of light, which was a shame, as it was not without its challenges, such as his explanation for why light might bend when passing from air to water. According to his theory, these light bodies should be subject to the same physical laws as any other projectile. And so with this in mind, he began to imagine the moment of the light's impact upon the water's surface, rationalizing that as the particle moved through the air, it would experience no net force that might move it in any particular direction. But when it closed in on the water's surface, this slight imbalance between the density of the air and the density of the water would lead to a slight acceleration, having gravity pull the particle down towards the water's surface. This then giving rise to the refraction that we experience as light's familiar bending. As an explanation, however, it required that light must accelerate into water rather than slow down. The counter to which was put forward by Newton's most notable opponent on the topic, Dutch mathematician Christian Huygens, whose theory of light waves suggested that light would slow when encountering water, though experimental evidence would not be possible until 1850, a near half-century later. Thus, it would take the efforts of the lesser-known genius Thomas Young to devise an alternative approach to the problem. Young's interest in light had come about as a result of his medical studies, though it would have initially been an understanding of sound that inspired his 1801 experiment. As sound waves, or any wave for that matter, move about the medium of their environment, they tend to bump into things, with waves inevitably crossing back through one another, an attribute that tends to cause familiar patterns to emerge. The easiest way of envisioning these is by imagining the ripples that occur when a pair of stones strike the surface of a pond at the same time. As each splash ripples outward, waves pass through one another, causing the surface of the water to amplify a patchwork of troughs and crests called an interference pattern. And it was Young's idea to seek these interference patterns within the nature of light. Like Ibn al-Haytham, Young was able to force light through a single point cut from a sheet of paper that covered a window. Then, by placing a card vertically down the centre of the hole, he further split the beam into 2 very small and very close equal beams of light. His thinking was that if the light did in fact move through space as particles did, then he should expect to see two distinct clumps of light, where each beam of particles came to land, just as sand would beneath the hole of an hourglass. But if light were to instead move through the holes as waves, then the two beams would disperse in equal directions, resulting in the familiar interference pattern. And to his amazement, there it was. A band of alternating light and dark lines that could only come about as the result of two interfering light waves. Irrefutable evidence that light did indeed act like a wave. And thus he had invented the famous, well, actually, at this point it was still the less famous single hole with the small card across the middle experiment. Not very catchy, I know. But essentially this was it, the famous double slit experiment. And if you're not impressed by this, don't be downhearted, there is still a part 2 yet to come. Though sadly for Young, as popular opinion refused to detach itself from the powerful influence of Newton, the experiment would be, for the most part, dismissed. But as time passed, and technological discoveries began to compound, it was Young's experiment that stood the test of time, so that by the end of the 19th century, with the coming of thermodynamics and electromagnetism, science had entirely adopted Young's discovery. Light was undeniably a wave, but the question which remained was that it was a wave of what? Good morrow, fellow humans. Sean here again. Lovely to spend some time with you. I just wanted to let you know that this week is part 1 of a 2-part episode, so I'm not going to keep you any longer. I'm just going to let you know that the second part of this chapter is going to come out very soon. We're actually going to post it next week, so keep an eye out for that, and we'll do the video episodes after that. That's all for now. Much love, and I hope you all have a wonderful, wonderful week. All right, bye-bye.